So hi, welcome. We're gonna wait a little bit more for everyone else to join, and then we're gonna start. Okay. They left. They left. Okay,
Armin.
but I'm gonna start. I'm gonna start anyway. Okay. شروع کنم؟
بذار من یه پیام به آکاش بدم
باشه
ببینم اگه
پیام.
چیز نبود.
Okay, so I'm Jan. Could you please start recording? Today we want to talk about this incredible, interesting paper called Empirical Design in Reinforcement Learning. And it's been done by a group of researchers at the University of Alberta. And basically, the whole gist of this paper and what we're going to talk about shortly is how we can make great empirical practice and great empirical experiments in the reinforcement learning setting. So you want to do an experiment, you want to see if your agent, your algorithm, or whatever method you've developed works well. There are some serious considerations they need to make because reinforcement learning is a bit different from other parts of machine learning, like supervised learning, because in supervised learning, you have a test set and you have a training set and everything's just separated, everything's nicely uncorrelated, and you can sample IID from your data set. You can't do that here. You're stuck with an agent that's working with an environment and it's generating data online most of the time. And that data is correlated. You cannot just do the normal statistical analysis that you normally do on those data sets in this setting. So we want to talk about those considerations and why the authors actually cared to write this paper in the first place. And I think this title sums it up really, really well. Reinforcement learning and empirical science. And it draws a tangent and it draws this connection to another sort of example. And I'm going to read this example and we're going to discuss it together. So I'm going to read it out loud and we're going to talk about it. So it says, imagine an animal learning laboratory where we study how quickly rats can learn to navigate a maze. We place an individual rat in the maze and record some demographic details, its height, weight, age, sex, and so on. So you have a rat. It's in some sort of maze. I'm going to bring that maze back. Where is it? For example, you have this maze. Forget that there's a graph here. And the mouse or the rat is trying to navigate the maze and get to a goal, probably some treat. And we want to see how it's behaving. And you have a bunch of features that you're recording from it. Its height, its weight, its age, its sex, so on, okay? And we put a block of cheese at the end of the maze, and we're trying to understand how it's behaving. And what we're trying to measure here is how much time it takes for the rat to complete the maze, so time to completion. And some other metrics like the number of wrong turns taken and some other things that we can think about. And the point of this example is to show that there's so much variability going on. I'm going to skip to a graph here that I think is interesting. If you look at this graph, this is real data of performance of rats in a maze. So these are episodes, and episodes are basically how long it took for the rat to get to the cheese from the starting point. And yeah. Oh, Akash wants to join.
Yeah.
Okay. Hi, welcome. Hi. Okay, so I'm going to do a little recap just to quickly make him understand what we're doing. We're talking about this paper called Empirical Design and Reinforcement Learning, and it's basically trying to give us some gauges, some measures of how we can do good experiments in reinforcement learning. And the paper starts with an example of a rat in a maze. Where can I find the maze? Yeah, imagine you have a maze. The rat starts at the starting point and wants to go to the goal. And we're trying to measure its behavior. And due to many, many factors that complicate measuring the rat, for example, the difference in the mood of the rat each day, or how well fed it was, or what sex it was, or what weight it had, or and so many other things, you're going to see a lot of variability in the performance of the rat. And so just having one or like a few runs or a few instances of the performance of the rat is not going to really give you a clear indication of how that agent is performing. And to your left, you see another RL agent, in a maze. So it's a simulated environment. And you see this so much variability. So this black, or maybe it's very dark blue, line represents the average performance, discounted return. And you see all the other instances just right in front of you, and you see so much variability. Some of them just catastrophically failed right here. Some of them succeeded really quickly. And then on average, you see some mediocre behavior. And if you just try to naively report the mean behavior and call it a day, then you'd lose out on all this rich information. So the main point of this paper is that you need to be really careful what you're reporting so as not to be misleading, and so as to keep your work scientific. Okay. So I hope everyone followed me as I was discussing that. And let's talk about some of the points here. And this is one of the points here. The aim should not be to show an algorithm is good, but rather understand an algorithm's properties, potentially relative to other algorithms. So the paper tries to distinguish two things. I'm going to read this again. The document makes a distinction between scientific studies and demonstrations of impressive engineered systems. So you basically have two paradigms here. One is you want to see what's possible, and you want to show, okay, we made a new algorithm that beat Lee Sedong in Go, okay? And that's AlphaGo, I think. Or we have another algorithm called AlphaZero that did this, and that's what's possible. But if we want to understand the algorithms, and that's I think the main concern of the writers, the authors here, you need to have a different approach, have a different way of thinking. Is that it should not be, you don't want to show that an algorithm is good, and you don't want to base your writing around that, but you want to show, you want to think of it as an object that you're trying to understand, whose properties you want to understand, and you want to compare it to other objects, other entities. Here they are algorithms. And it gives some definitions of what an algorithm is, what an agent is, and what a fully specified algorithm is, and what an unspecified algorithm is. I'm not going to go into too much detail. By algorithm is basically, we mean something like a strategy to learn. So like DQN is an algorithm. It's a strategy to use the experiences that you amass from the environment and you learn, basically. And a difference between a fully specified algorithm and an unspecified algorithm is one where you supply the algorithm with specific hyperparameter values in this case. But in this case, you don't. You don't know the hyperparameters. You're just saying, okay, I'm just using DQN, so that's unspecified. But if you say I'm using DQN with step size, blah blah blah, learning like blah blah blah, then you're talking about a fully specified algorithm. Okay, and yes, let's move forward a bit and talk about what we can do. So, okay, you have this mean, and it's not that indicative of your distribution. What can you do then? Okay, just look at the whole distribution. So, the next point that I think we can talk about is performance is a distribution. So, the performance of an algorithm, an RL algorithm, is a distribution, and it varies with hyperparameters. So, in the case of a rat, there are so many hyperparameters outside of our control, like the weather, the laboratory conditions, if the rat was fed or not, whatever it felt at that moment. We can't control that. But in the RL setting, we basically control everything. And that's a double-edged sword. But because we can, control these things, sometimes we can just look at the whole distribution. and the whole with, like, for example, if you look at this figure, it talks about the performance distribution of DQN on Monte Carlo with step size 2.91. So you use the other instances of the hyperparameters and you fix this one, and you see this whole behavior. It's not just a normal distribution, it's bimodal, and it's a bit skewed. And if you look at the mean, it's not going to tell you much because of the way that the distribution works and how it looks like. Okay, any questions or any concerns until now? We can have a discussion. This is not a pure it's not just a presentation. We can discuss if you like. Okay, let's move on. So we have this setup. Of course, yeah. Go for it.
Can you explain this figure a bit further? Like when it says it's bimodal, I don't understand exactly. Like, is it the whole? Like we have run a bunch of different networks, and this is the return of them, or a single network? Like,
okay. Let me read this exactly, and we talk about it. That's a great question. The performance M is the final performance of the agent after 100,000 steps of learning. The density around values of M represents the probability. Okay, so you've basically fixed one hyperparameter, and you've let the other things vary randomly, and you've done that many times, and you've plotted the return, and you get this distribution of return for this fixed value of step size, and everything else is varying. And it says this density is estimated using 1,000 independent DQN agents. And when it says independent, it means the random weights were chosen randomly, everything else was chosen randomly, except the step size. Okay, does that make sense?
Yeah, thank you.
Okay.
Well, is it okay if I add something?
Of course, yeah, go for it.
So it's also possible to have a bimodal performance distribution, even if all the hyperparameters are fixed, and the only thing that's changing is the random seed. Especially in online reinforcement learning, you have problems where you might get lucky in some seeds and learn about some very good behavior very early or very late.
Yeah. And
that leads to bimodality in behavior, even if everything is fixed except the random fixed seed. That's it.
Yeah, and I think in that case, the random seed is affecting how the environment is working, right?
No, so the random seed is, well, it can be put in multiple places. Usually it's put in the random initializer of the neural network.
Yeah.
And also the random, the random number generator for the epsilon soft policy.
Yes. Yeah. And the environment itself as well, if there's some stochasticity in the environment.
If the environment is stochastic, yes. But the environment need not be stochastic for bimodal behavior.
Exactly. Yeah. Thank you for your addition. Thank you.
In that case, the random seed is going to be a hyperparameter here?
No. The random seed is just like initialization of your network.
Yeah, but can we consider it as a hyperparameter?
Well, that's very bad because then you can search and optimize over it, but that's not really in your design. That's just a part of the aleatoric uncertainty in the world. That should not be affected. Searching for seeds is very bad. I think something in this paper talks about that as well.
Yeah, that's a great point. This discussion is a bit semantic, but I agree with Farham in saying that it's good to distinguish these two things. If your definition of hyperparameter is choices that you need to make in the design of the algorithm, then probably you could say that that's a hyperparameter. But because we're specifically talking about hyperparameters in a different sense, and we're going to get to that, we sort of say that's not. Yeah. Okay. So, let's move on if you don't have any other questions. Okay. Perfect. Okay. So basically, we see that, okay, this mean is not a good statistic, and it doesn't tell us much, and the distribution is telling us a lot. But we can't always, just do this and look at it graphically. We want to have some other statistics that we can work with more systematically. And so the rest of the paper is going to talk about this, reporting variability in performance, and the different measures, different statistical methods that we can use to report how an agent or an algorithm, let's say, it's better to say an algorithm, is varying in performance, and how we can showcase that. Okay, so you can always do this brute force, and then you get a graphical representation. You just look at it, but we want to have some more quantitative measures of performance. So, okay, so it at first it just talks about it calls it a distribution agnostic approach. Is to look at the percentiles. So if you remember from statistics, you have these, let me look at this box plot. Where was that? Yeah, this is a confidence interval, I know, but let's imagine it's not, and it's a box plot, and you have these percentiles. For example, imagine this is the mean, and that's the interquartile distance, and that's the 25th percentile, and this is the 75th 75% percentile, and so on. So we can just look at that. That's one way. Where did I go? Yeah, here. To say, okay, I want to look at the distribution of the algorithm, and see how much of the distribution fits in some percentile, and that's one way of looking at it. Another better way.
Sorry, but I thought that the box plots are based on modes, not means. Why?
Based on what? Sorry, based on nodes.
Maybe based on
the median. You mean?
The median. The median.
I misspoke. Yes, I meant the median.
Oh, but in the plot, in the picture, it says mean.
Well, that's a confidence interval. I'll talk about that. I said, yeah, yes, I misused the graph. There were not supposed to be box plots. I just wanted to showcase a box plot. Yeah, yes, you're right. I misspoke. Yeah, I didn't mean a mean, but a median. Yes, for the percentiles. But for confidence interval, we'll get to that. Let's talk about something that the paper calls, or that is called, tolerance intervals. And I think it's really important to distinguish the difference between a confidence interval and a tolerance interval. Let me first talk about a confidence interval. Let me come here and use that graph again. Forget about these differences and imagine just this is a confidence interval. A confidence interval basically tries to give you a measure of how confident we are about the position and the range of a certain statistic of our population. So at first, you have to choose a statistic. So here we've chosen mean as our statistic that we want to see how confident we are about. And then we can use bootstrapping, we can use the student t-test if to see, to take a interval and see how it's behaving. But the main point is that you're measuring your confidence about a certain statistic of the distribution. Here is a mean. Could be the variance, could be different. Okay, so that's a confidence interval, and you choose a confidence level. For example, alpha equals 0.05 means I want to be 95% sure that the mean is in this range. Okay, so if I say that this is the confidence interval, I'm saying that basically the mean with 95% probability is somewhere here. Okay, but a tolerance interval is a whole different thing. A tolerance interval is trying to showcase the variability of the data itself. How much with some confidence level. So this confidence level is the same. It exists in both the confidence interval and the tolerance interval concept. But with some confidence level, we want to see how much of the 95% of the data fits into what interval. I think if I can show you here. So, okay, here. Let me read this for you. Tolerance intervals for the discounted return of DQ1 on mountain car over 50 runs with alpha equals 0.0.5. Okay, so this tolerance interval is basically saying this is the with this probability. Where is that? With 95% probability, the whole variation of your agent, your algorithm, is going to be in this sort of range, or here, different values. But if we were talking about a confidence interval, we were just talking about our confidence of the mean, and that's a whole different thing. We don't necessarily just want to look at the mean, as we discussed. Could be misleading. That's good. We can look at the mean as well and how confident we are about its location. But this gives us a picture of the whole data set of runs that we've collected, and we want to see how variable they are, basically. Okay. And what's the difference between this and a percentile is this confidence level. And of course, there are many formulas and technical details that I won't get into. To be honest, I'm not that well versed in them, but that's basically the whole gist. And if any of you have any comments, of course, I'm happy to talk about it. Or any questions. No?
I don't understand how we get this confidence intervals.
Confidence intervals, how we get them? You mean how we calculate them? Okay, so there are many approaches. I think the most straightforward approach that I can talk about is the bootstrap. Let me bootstrap aggregation. I don't know. Well, bootstrap. Yeah, bootstrap. Yeah, okay. I want to show you in the text. But basically what you do with bootstrapping is that you have a bunch of data you've collected, okay? And you get n measures of performance for the algorithm with n random seeds. And then you try to resample from that n many values, and you sample exactly n values. So imagine you've collected 50, like you've had 50 runs with 50 different seeds. You've collected 50 performance values, like this, okay? And then you start sampling from those 50 values with replacement. And after you do the sampling, so you've sampled those values that you've had. And then you repeat this many times, 10,000 times, whatever, many times, and then you get a distribution. Let me. Confidence intervals at bootstrap. If I can show you a picture here, yeah. So basically, what you do is you start.
We don't have picture.
Oh, you don't have it?
No.
Do you have my screen, guys?
Yeah, but it's just a PDF.
It's just a PDF. Okay, just give me a second. Let me.
Oh. Okay.
Maybe it's my connection, because I can see that it's changing.
Yeah, now we have it. Go.
You have it? Okay, perfect. Okay. So imagine this. You have you basically get them. For example, imagine you want to look at the confidence interval of the mean. You calculate the mean for all those new resamplings that you did, and you start plotting them. You start getting a histogram, and you get a distribution. Okay, you get a distribution of those resamplings from the 50 numbers that you had. So you have a fixed list of 50 numbers. You sample from it with replacement, groups of 50, and you do it for like 10,000 times, And for each resampling and the groups of 50 that you did with replacement, you calculate the mean of that. And it acts like a random variable. It might go here, might go here. And then it gives you like a distribution like this. And you choose places that account for 95% of the area under the curve. And that's your 95% confidence interval that your mean is likely to be in. That's the bootstrap method. And then you have this student T. Oh, why did I stop sharing? Then you have the student T approach that needs you to assume that it's a Gaussian, and many other ways. But basically, it's trying to find a measure of how confident we are by looking at how the mean could change from the data that we have. Does that make sense?
Yes. And so for the next part, for the tolerance interval, we fix the alpha, and then we just sample from those results that are in this specific threshold, and then we change
for tolerance interval, we don't use a bootstrap method. It's different. I'm not exactly sure about the details. It's not, but I know that it's not a bootstrap method. Yeah, it's different.
Okay.
Yeah.
Thank you.
You're welcome. Yeah. Thanks for the great questions, by the way. Okay, so to recap, we were trying to report variability in performance. Some of them was looking at the percentiles, looking at tolerance intervals, which is basically the variability of the whole data of the performance measures that we've collected, not our confidence. It could also be a confidence interval of the mean. That's something that we can also look at. And sometimes it's also good to look at the median performance instead of the mean, because the mean is not it doesn't actually exist. The mean performance, the mean run, is a made up thing. It's an abstract thing that we've made by adding up different runs, and it doesn't represent an actual run. But the median does. The median is an actual run, and sometimes it's good to look at the median to get an understanding of an actual run. And you see, the mean is this very smooth thing, but in reality, none of these runs are really smooth. You see, this median one is quite variable. And so that's also a good thing to keep in mind, that sometimes it's good to use the median. Okay. Okay, so I'm going to not look at this part because it's just the details of how to do a student T with what a confidence interval, but it's good to look at. It takes a while to talk about. Yeah, let's move on. Okay, so basically it's talking about a confidence interval for the mean and how you can, oh my God, do you have this problem that it's pixelated? Okay, can you hear me?
Yes, it's pixelated.
Okay, so thanks for the feedback. I'm having some trouble here. Give me a second, sorry. For some reason it's crashed and the PDF is not opening, so I need to open a different tab. Okay, just a moment. Okay, let me share again. Okay, so can you see my screen now?
Yep.
Okay, great, perfect. I think Parham was talking to us from the moon. Okay, so we talked about confidence intervals, tolerance intervals, and I'm going to skip over this part. It's just the details of how to calculate the confidence interval. Now, let's talk about some of the differences between the different types. So there's a trade-off that you're making by using different methods of calculating confidence intervals. If the method that you're using is too sensitive, it requires many more samples to get a tighter interval, then you're going to trade off a lot of compute time that you need to spend to get it right. So here, the Bernstein method that they've used doesn't really give you a very, very narrow range for the mean, because it needs a lot more, many samples to become narrower, to converge. And something else that I should have mentioned that I forgot is that when you collect more and more samples for the tolerance interval, it doesn't converge, it doesn't become narrower, because it's not a measure of confidence, it's a measure of variability. So, but for the confidence interval, the more you collect samples, the more it converges and the more tighter it gets, because it's a measure of confidence. Okay, I'm gonna skip
Sorry.
this part. Yeah.
In the picture of confidence intervals, why does the mean change for the plot in the right?
Wait. This one that's pixelated?
No, not this one, not this one. The box plot.
The box plot. Why does the mean change between the?
If you check for the part A, all of the means are almost the same. For B, the mean of the Bernstein one is a bit higher. That doesn't make sense if it's the mean.
That's a great question. I hadn't noticed that. Let me take a look. Okay, so it says confidence intervals with 10 runs, confidence intervals with 50 runs, and let's read it. Maybe the answer is in the text. Confidence interval about the mean total discounted return on the DQN. Long-tail behavior in the performance distribution violates assumptions for the student T distribution, whereas the percentile bootstrap fails when too few samples are used. So it's talking about that. We include the standard error only to highlight the falan. Okay. Implicitly, using a standard error is like using a student T test. In this instance, for n equals 10, the standard error represents a student T. And okay, that doesn't make sense to me as well. You're right. Maybe it's a mistake in the graph. I'm not sure, because there have been a few mistakes in this document that I've spotted. Maybe it's a mistake, but it doesn't make sense to me either. You're right. They should be at the same mean, because it's just the mean that we calculated in the sample mean. Okay, I'm not sure. Maybe it's a mistake in the graph, but that's a great catch. Thanks for mentioning that. Okay. All right. So this remark is talking about being careful about the distribution of your the underlying distributions of your performance. It says that if it's not very close to a Gaussian, don't use the student t-test, because the student t-test assumes that your underlying distribution is a Gaussian, is normal. And yeah, so we need to be careful about that. Okay, and now it talks about, okay, why do we need so many runs? Can't we just do 5 runs, 10 runs, and call it a day? And then you get this plot, which is really interesting. This like long tail of this distribution, this is DQN, by the way, in Puddle World. And this long tail of this distribution is telling us something. And what it's telling us is that you can't be so sure, because you get these outliers that are really, really bad, that just fail completely. And if you want to understand an algorithm, you're not just trying to show that it's possible for it to learn. You want to show what its properties are. You want to understand it in a scientific way. Then you need to look at these edge cases. And these edge cases are rare, but not so rare that you can just completely ignore them. But they're not so common to show up in just like using 5 runs, I don't know, or 10 runs. So you need to be careful, because these rare cases happen, and because these algorithms are highly variable, just like the rats were highly variable, because there's so many different conflating variables that are contributing to the performance of any algorithm or any rat in this case. It's just the complexity of our problem is just much higher. Okay, and because of this, it's giving us a heads up and says, okay, we need to do many runs. Okay, and it talks about the different types of solutions to how we can tackle this. Maybe sometimes we can't do many runs, or like we want to ignore those bad runs. How can we do that? It talks about like using the interquartile mean, which is the distance between the 25th percentile and the 75th percentile. And because you're basically in the middle around the mean, you're getting rid of those outliers. And it's quite robust to outliers, because you're just getting rid of them. But you need to be sure what you're doing. If you wanna ignore the effects of the outliers, maybe that's a good idea. But if you want to give a whole picture about how an algorithm works, then maybe you should have second thoughts about that. Okay, so let's take a look at this one. Okay, let's talk episode cutoffs. So in different runs, in different environments, for example, let me search another one. For example, frozen lake environment. Yeah. So you have this, for example, frozen lake, where basically you have an agent and wants to go get a gift, and that's when the episode ends. And you have these puddles, or I don't know, lakes that it can fall into, and it will reset back into the first position. And technically speaking, an episode could take infinity. It could just be extended to infinity. It could never end, because it could just run into a loop and never end. And we don't want that in training, because, well, that's an infinite loop, or it's a very, very long episode, and you're not getting any signals, you're not getting any reward, so you can't update your agent. So normally what we do is we introduce a cutoff. Of course, you're familiar with that already. And with the cutoff, there are some considerations to be made before you do that. The first thing is that you make the environment easier when your cutoff is really, really short. So basically, you don't let those really, really outlier cases to occur, because you're ending them prematurely. You're not letting them happen. And that's why it becomes easier, because everything gets tighter. Everything, all the performance of the agent looks neater, because you're getting rid of those outliers, and you're not letting them happen. Okay, and you see here, if we take a look at the different cutoff points, you can see that, like, if you put the cutoff at 200 time steps, it's basically a complete, like, it looks like a straight line. It's not, but it looks like a complete, like, it's not a straight line. I mean, there's no variability. You don't see any shading. Then you have a cutoff of 500. You can see some shading, but barely any. And then you go to a cutoff of 1,000. Oh my God, you can see that there's so much variance going on here with the different values of cutoffs. And so you have to be really careful about how you think about cutoffs. And if you make them too short, you're making the problem easier, and you're not getting the whole picture again, because you're getting rid of the variance that you have, the variance of performance, because you're not letting your agent run for long. Unless, of course, your goal is to show how the beginning stage of the learning of the algorithm works. Then in that case, maybe that could make sense. Okay, I'm going to take a look at this key insights, and we're going to wrap it up for today. Let's read each of them and review what we did today. So these are key insights about evaluating a fully specified algorithm. So you have a base, you've chosen the hyperparameters. So we've talked nothing about hyperparameters yet, and here we're varying the seeds. So in this paper, the random variables of a network are not hyperparameters, because if it were, then it wouldn't be a fully specified algorithm. Okay. Number one, a single run of an agent can be informative. Consider visualizing individual runs to gain some understanding of your algorithm. So it's okay to understand your algorithm just looking by a single run. It can be informative, but it's nothing more than that. It's just for you. It's for your personal use. And that's it. Okay. Agent behavior with the same algorithm and environment can be very different across random seeds. Consider reporting this variability using sample standard deviations or tolerance intervals rather than just reporting the mean or median performance. We discussed this. The median or the mean are not at all representative of the performance distribution of your agent over random seeds. So, report different things. Report a tolerance interval. Report different statistics that show the variability of your agent over random seeds. Yeah. Confidence intervals around the mean primarily tell us about our certainty in our mean estimate, not about the variability in the underlying agent. So don't confuse the confidence interval of the mean to showing the variability of your agent, because that's not at all the case. Because if you run it enough many times, your confidence interval will become thinner and thinner and thinner and tighter and tighter and tighter. So it's not doing that. If you primarily care about understanding mean performance, then report means with confidence intervals. If you care about the behavior of each agent, not just the mean, consider reporting tolerance intervals. Okay, so that's an important distinction to make. In general, we advocate that you do not report standard errors. Okay, so standard errors are basically a statistic of the standard deviation of the sample. Okay, they are like a low confidence interval, and it's what does that mean? Let me take a look at this one. So if you look here, this standard error is much tighter because you're just using the sample itself. Okay, and when you're using the sample standard deviation, it's going to be much tighter than the actual confidence interval that you're going to get with bootstrapping or student t-test. Student t distribution, excuse me. Okay, and so it's just going to be less informative. It's just going to make it look like you're more sure about something that you're not so sure about. So they just say, okay, don't do that. Okay, the required number of runs depends on your performance distribution. So if you just take the number 30 and say, okay, I'm just going to do 30 runs, or I'm going to do 50 runs. You have a trade-off here. Well, it's runtime. You're using compute, and okay, maybe Frozen Lake with DQN is not that computationally expensive, but have fun, doing Atari like that. So you have to be really careful and understand how many runs you need to do to be sure, and then do them. And so it needs to be an informed decision, not just a decision that you make on a whim or using some rule of thumb. Okay, and it's clear that in almost all cases, 5 runs is insufficient, but sometimes 30 runs can be insufficient if the distribution is heavily skewed. What does that mean? The meaning is that if it's really, really skewed, then you might need 50 runs to get these really, really rare, horribly performing agents or algorithms, or specified algorithms, yes. So you need to consider that. So don't use rule of thumbs, be informed and try to understand your performance distribution. Okay, consider reporting performance versus steps of interaction rather than performance versus episodes. Okay, this is something I skipped. Let's take a look at this Frozen Lake. Every episode terminates if and only if the agent reaches the goal. Okay, and let's forget about cutoffs for now. So if your agent doesn't reach the goal, the episode has not ended. So your episode becomes longer. So if you want to have a run and say, okay, I'm going to run this agent for 10,000 episodes, but you're not, and you do that 2 times, you're going to get different amounts of interaction with the environment. Maybe in one of those runs, you had many bad runs, and you had more interactions with the environment. And on the other hand, in the other one, you had very, very good runs, and you had fewer interactions with the environment. And so you're not getting a fair comparison there. You're comparing apples and oranges. So you should you should think about using steps of interaction, basically time steps, rather than episodes. Okay, so this choice ensures every agent receives the same number of samples. Okay, let me read 7. Deliberately choose a number of steps of interaction to reflect early learning or the ability to learn the optimal policy. So this means understand that if you want to talk about or look at early learning, okay, limit your steps of interaction. You don't have to run it until it converges or it learns the optimal policy. But if you want to look at the optimal policy, then okay, increase the number of steps of interaction. Okay, don't just blindly use what other people did before. And if you make your episode cutoffs too short, then you're gonna get really tight, really tight variability. And that's really misleading because you're not letting the variability occur for you to see it. Okay, so that's about it for today. I think we can have 2 more sessions because this is 61 pages. It's quite long. And we can talk about hyperparameters next, and how we should think about them, how we can deal with them, how we can try to understand and report them. Okay, so if you have any questions or discussions, I'm here.
Hey.
Hi.
Very nice talk.
Thank you.
Excellent. I did want to ask, so if you want to eventually use these larger environments like Atari, and you still have the same issues, how would I do something scientific with Atari and still, have 5 seats or have 1 seat?
I'm not quite following your question.
Yeah, sure. So say if you want to do Atari experiments, and these are large, and so one of the main takeaways is that you should have more seats.
Yeah.
But you cannot have more seats in Atari. Now.
Yeah. Okay, it's a great question. To be honest, I haven't thought about it that much. But my guess would be is that you can try to look at other things that you can change, maybe. I'm not sure. Maybe you can give us your insights. I'm not sure about this question.
Hi.
Maybe someone
I
else.
think I might have an idea for that. So along some papers, what I've seen essentially is like they entirely retrain the whole algorithm and then test it in the same seed. So like whole of the retraining is like done again. So that's like considered as a different seed than whatever you did previously. Does it make sense?
So if I understood you correctly, you're trying to say that you just fix one seed, and then you retrain with different initializations of the network?
Exactly. Yeah.
Okay.
Yeah, that's the problem I'm also facing right now. So like I'm also working in some kind of discrete RL case environment, but the thing is like all of the recent papers, particularly like in the domain of like offline RL things, I don't see the confidence interval being reported at all. Because in most of the discrete state things, the common observation is like sparse reward setup. So the key metric is like just success rates. So how do I go about reporting success rates? There is like nothing about, they just report the mean success rate of like maybe let's say 5 seeds. That's it. I don't think it's a true representative of like the whole thing at all. But then they still do that.
I see. What do you think about that, Parham? I think you have some ideas.
Yeah, sure. But thanks for the talk.
You're welcome. Thanks for your input.
I think things like success rates are here introduced. So, okay, my insight is that we have to change the things that we are asking. So if we don't have enough data to talk about performance, then we shouldn't talk about the performance.
Okay, yeah.
And here, success rate might be a softer example, as in, well, I don't know how good I did, but have I been able to do it at all?
That's also one another way. So like you can go about showing, how good your learned representation is, or, some other metric which lets you actually take the decision, the whole concept of like the algorithm which helps you make the decisions. So like there is like some other solution to it. But again, the problem I see is like they mostly handpick these results, it's like hard to reproduce is like the whole problem. This is inclusive of me. I also do that. I'm not just criticizing the whole community. I also do that. But then you see the whole problem there is like how to reproduce such kind of things is like kind of hard.
I see. Well, I think in the paper, dear Akash, the authors they talk about this exact thing, and when Parham said that, I just remembered. They say that if you can't report something and you don't have the compute for it, don't report it. That's that's
sure. No, that's a good strategy as well.
Yeah. Yeah. So if you can't be sure what you're talking about, don't talk about it.
Don't talk about it. Not a bad idea.
Yes. Okay. Do you have any other discussions or interesting points you would like to talk about?
No, that's it from my end. Okay. But yeah, thanks again for that.
Thank you for joining. I had a wonderful time talking to you guys and presenting that paper. I would be interested in having some sort of discussions about these things, maybe challenges that each of you are having in your, in your projects, and we could maybe brainstorm and think. That would be an interesting thing. Probably I'll talk about when we can do the rest of the paper. Probably that it needs like 2 more sessions. Maybe I don't think I can condense it into another one. It's a lot. It's dense, and it has many appendices as well. Maybe we can think about looking at the appendices. So I'll talk to you about that. If you have any other comments or interesting things to say, I'm all ears. If not, have a great day or night, depending on where you are.